So I go?
No. You need to introduce first.
Yeah.
What are you doing? Don't move the laptop.
I didn't move. Good morning, everyone. We're Osteobotics from Shajeh Boshan Studio. My name is Sulaf Aburas, and my colleagues are Maria, Yani, and Mattia. Where's the sound?
It's not
There's no
playing.
sound.
No, here, the cable is here. There is not sound. Why? Okay. So,
There's a problem.
it was working.
Mattia.
Yeah.
No. Yeah. But it's not reading.
Okay. There you go. No, it's not. Just play it.
No, don't play it. Look. Don't play it. Look, it's not reading.
Is it on the microphone?
Yeah, it's done. It's because you need to play it. Can I?
Just the
Play it?
audio. Yeah, just the audio.
Then.
There's no audio.
There's audio at our end, it's your end. I've already tested it twice.
Okay, wait 1 second then.
It's not muted somewhere, is it?
Yeah.
It's coming through the headphone jack. I fear it's going to come out very loud. Ah, that's right. It's trying to go through the HDMI. Turn it down to go down to the through the headphones.
Okay.
Turn off the audio. Yeah, it will do that. The audio will it selects.
Speaker.
Go back to the normal speed.
Okay. Go. Play.
No.
Yes.
No, it's too slow. Right.
You're changing the Our thesis is on automated robotic fabrication for temporary architecture. At a minimum rate, there are 1,418 temporary pop-ups currently in London. All the waste from these temporary architecture, along with the permanent ones, contribute to 40% of the overall waste in London, making them the highest from the overall total waste. 70% of this waste ends up in landfill, while only 11% gets recycled. The London municipality is aiming to reduce the 70% to 20% and to increase recyclability from 11% to 25%. Therefore, we're proposing a flexible automated robotic arm fabrication system, which exploits phase-changing material and utilizes robotic arms intelligence by executing accurate, repetitive actions. The system, enclosed in a mobile cell, allows the fabrication of a continuous lattice structure that can be melted and reused again or just be left to biodegrade. The dynamism and reusability of our system result in a variant temporary architecture applications, where the manufactured lattice is manually assembled on site using heat only. Over the centuries, industrial robotic arms have been trying to replace human force in factories by only doing things faster, stronger, and more accurate, but never replace intelligence. Since the use of industrial robotic arm in the factory, until this day, they've only been doing things more accurate and faster and better, but not yet integrate the intelligence of the material within the material at hand. Thus, architects look at robotic arms and understand their different parameters to use them differently. Architects such as Gramazio and Kohler try to understand the parameters of this tool, and rather than use it as a fabrication tool, try to integrate it in a bigger picture where the material is thought as intelligent. Thus, we're aiming to shift this paradigm of the industrial robot being just as a force replacement in factories and try to integrate it in a bigger picture with the material. So why are we using robotic arms? For their accuracy and simple repetitive actions and customization of their end effector, to integrate them with the material intelligence and to facilitate a new novel kind of architecture. As a phase-changing material, we focused on plastics. Plastic has its use in architecture since the 1950s, where architects were trying to produce a continuous free-form shape. Yet, they were only able to achieve it in panels. Even until this day, panelization of plastic came a long way, where they tried to triangulate to produce free-form shapes or cast all the plastic at once. But none of these projects really look at the phase-changing materiality of plastics and what it can be done with it, such as this project where the material is actually pulled. So we're aiming to use phase-changing plastic with its material intelligence to create a continuous structure.
We are using polycaprolactone. Polycaprolactone is a biodegradable polyester, which melting point is 60 degrees. The most important characteristics of this material is that it's biodegradable, that is reusable, it's high abrasion resistance, and it's high elasticity. How is the phase changing of this material? Initially, it comes in those white granules that becomes a viscous mass by heating at 60 degrees. This material can be cooled down to get the solidified state, and can be melted again to reuse the material just by heating at 60 degrees. So the loop can repeat it over and over again. So having that in mind, we start to program our polycaprolactone. So the first experiments that we did, we used the solid granules, heating it by 60 degrees, getting the hot viscous mass. This viscous mass was deposited in acrylic rigid plates, in 2 acrylic rigid plates, that then when pushed inwards and then pulled outwards, reaching a position or reaching a length, cooling it down to get a pulled beam. So the first experiment, we did small-scale experiments trying to fuse the material with other materials and trying to look at the parameters of temperature and quantity, and then trying to scale up the most successful experiments and looking again at the parameters of temperature versus quantity.
The physical experiment showed us that many parameters are involved in the material formation. For this reason, we developed a material simulation that allows us to study this parameter individually. First parameter that we studied is the particle thickness. So the number of neighbors that are connecting each other are able to control and determine the section. Another important parameter is the plate's thickness. According to how much material sticks on the plate, we can have a big section or a small section. So we understood by this that the plates can change the structural behavior of our beams. Another important parameter is the initial material distribution that controls the amount of holes that we generate in the beams. We can see on the right side the formation of holes, while in the left side is uniform and doesn't have holes. Last parameter that we studied is the viscosity of the material. More dense part has more weight and they collapse on themselves. This doesn't allow the section to formate properly.
After looking at all of those material simulation parameters, we were evaluating which is the correct deposition and the correct shape of the plate in which we need to use. So we got the conclusion that the triangular deposition and triangular plate is the optimal because the surface tension is divided equally in 3 parts to get a stronger section. So we start those experiments with triangular plates, acrylic plates still trying to deposit in lines and in solid mass, getting a better result with solid mass. And also trying to get material continuity, we tried to explode or kind of pull a tetrahedron node, which we couldn't control really well. And also we had the issue of the rigid plates acrylic, so we couldn't get so well the continuity. So how to create a continuous and reversible material system? We came up with prefabricated nodes. So the first prefabricated node is a tetrahedron node that is made of polycaprolactone, is lightweight, it's a regular tetrahedron, and a polycaprolactone regular triangular plate, which has 5 millimeters thickness. And we are pulling beams from those nodes. The minimum extrusion length is 10 centimeters, and the maximum extrusion length is 60 centimeters. So summarizing, how is our technique? We are taking the solid granules, heating it at 60 degrees, melting them until getting the viscous mass, depositing the material on rigid plates or tetrahedrons, pushing the melted material inwards, the nodes, pulling the melted material to reach a position, cooling the material down to reach the beam, and the loop can be repeated to create the lattice. So it give us a cycle which leads to reusability. To demonstrate that the system can behave well, we did 2 kind of pulling from plates from the tetrahedron node and from tetrahedron to other tetrahedrons. Also, when all of the tetrahedrons are static, not doing anything.
Don't touch this.
So when all of the, I didn't do anything. Are static, we are closing the loop with the rigid plates. That's the use of the rigid plate. So we are move this a bit. It's okay.
Just don't touch it.
So we are pulling the beam from the face of the tetrahedron and heating when it's close to the next tetrahedron. We are heating the surface of that rigid plate. Using just heat only, we can close the loop.
As a structure methodology, we focused on lattice structures. We looked at their triangulation and how complex the joint can get, And how can we use the same material of the joint and transform, like in this model, a paper tube that is non-structural, very fragile material, to a very structural material. Moreover, we also looked at lattice continuity and how can we achieve that other than casting it or just using different joints. We looked at also lattice relaxation, and the reason we did that is because we want a continuous lattice structure that can behave structurally, not dependent on the element itself, but rather as the whole network.
So in order to create a lattice structure, we were evaluating with the small scale models different kind of branching inside the system and evaluating which are the constraints of our material physically to get the lattice structure. So those, why is me? So those constraints are angle tolerances, extrusion length, tetrahedron position, and taking in consideration as well the robotic arms constraints. So evaluating this, we know that the pulling of each beam has angle tolerances. So in each axis, X, Y, and Z, we have 45 degrees of tolerance to pull the beam. Also, we consider which are the best orientations in space of the tetrahedron. So the first position is the best position for arc point to the ground. The second position gives us opportunity for growing for upper structures. The third position gives us the possibility to join sides and connect ground with upper structures. And the fourth is a double tetrahedra that can give us more available faces to connect up and down. So after this evaluation, we start with our with our spatial primitives. So starting with the minimum column, we develop a core that should be tied twice in order to get a triangulated column. In this case, the length of each beam varies depending on the force that they need to support. We develop a catalog of our spatial primitives. The minimal diameter is 0.90 meters, and the maximum is 1.20 meters.
We studied how with our system is possible to generate a wall. The initial distribution of the anchor point control the way the wall can grow. And the second layer determines the kind of pattern that we can achieve. We studied three different types of wall. First, we tried to have a minimal wall of 30 centimeters. Second is a wall of 50 centimeters. And third is a wall with a 90 centimeters of thickness. We studied, moreover, how we can connect this wall together.
As well as we studied ceilings and domes and shells. First, we started to generate a flat ceiling, but we realized that our structure doesn't really work flat. So we used a mesh, we relaxed it, so the triangulation of those elements are in between the range of our beams, and then we developed units on top of that relaxed mesh. We developed 2 units. Those units are only triangulated by themselves. They cannot allow available faces for the next one. But then we moved forward and we developed another kind of units that have available faces to grow the structure. The first one allows the structure to grow linearly without any holes in the generated structure, while the second one allows the structure to grow radially and generating holes in between the structure. This is the catalog that we produced of the different single, double curvature, and shell of different primitives. And as you can see, different units generate different kind of structures.
Then we were evaluating the connection between columns and ceilings or walls and ceilings. So for this, it's really important to look how many available faces for connections are in ceiling and in the column. For that reason, we develop a generic funnel that can be attached to both structures and can be adaptable for different kind of ceilings and different kind of columns. So this is a kind of catalog in which it's perceivable that it can be adaptable to different kind of configurations.
These special primitives are evaluated from a structural point of view for the requirements given by our material. Thanks to the structural analysis, we understood that some of the elements in our lattice is both in tension and in compression. But what we observe that the material that we have actually generates kind of beams that are thin in the center, so are unstable and they work better in pure axial forces, or tension or compression. So we studied how we can achieve pure axial network using particle spring system. But we need to consider also the parameter of our material, the constraint of our material, angles, extrusion length, tetrahedron position, and robotic fabrication. According to do this, we developed a strategy where we are controlling the relaxation of the system, allowing only to those points that have more tension to move. So we are trying to reduce the singularities in the flow of the tension. We are studying also how, when we are going to fabricate the system, the equilibrium of each element works. So we separated in chunk of fabrication, and we are considering anchor point and load point, and we are analyzing the displacement of these elements in order to understand where the anchor point will be when we are going to overlap many layers of construction. So we get from here two important information: the distribution of the beams that are going to have more deformation, and the distribution of anchor points by overlapping different layers. We we compared the different networks and the behavior of different networks. In the case of column, the strategy was to try to find a network that needs less deformation to reduce the bending forces. We did the same studies also for the walls, and we observed that in the walls the tension configuration is more near to the starting configuration. A similar studies has been done for the ceilings, and what we observed here is that the ceilings tends to generate in the bottom part a concave shapes in order to support the loads. Similar behavior has been observed. Similar behaviors of the column has been observed also in the funnel.
In parallel with the material experiments and the primitives, we started to study like the robotic movements, constraints, possibilities, and limitations that we have. We started to see how the robotic arms are used in the industry. They are using them according to what is the usage of the end effector. The end effector, the customization and the possibility of it gives the robotic arm the opportunity to do different actions. So for us, the end effector, it's a mediator between the material intelligence and the robotic action. As long as we have a depositing system, a deposition machine, it needs to be developed. This is an extrusion machine that takes the material as granules and is extruded in 60 degrees in viscous mass. It's been used by a temperature controller, and we use an Arduino and a DC motor to control the deposition and the speed. So to control the speed of the deposition in order to have an automated fabrication system. The next end effector that was necessary was an end effector that can take the tetrahedron and place it and release it. at place. So it's like a system that it's an effector that can lock and unlock the tetrahedra and place it in position. Another effector is necessary is the plate end effector, the one that needs to connect two faces in between. It's a simple mechanical end effector that can change the plate easily and in a fast way.
So, how does our fabrication process work? The whole process is enclosed in a cell. The cell is mobile, with the minimum amount of robots needed for the fabrication to start. The fabrication starts by picking a node and then taking the node to the extruder by the robot, and then going to the anchor point and pull the beam and then freeze the beam by cold air. Once the units are fabricated, they are assembled on site by human workers using heat only. Once that architecture is done, it can either be shredded down and refed into the system or just left to biodegrade and produce biomass. To demonstrate this cycle, we did a prototype with an already arranged configuration of robots that we had to study and to fit into our system. These are the main parameters that played a big role into the fabrication process, as well as real-time parameters such as extrusion speed and deposition speed. A geometry was fabricated specifically for this arrangement of robots. As I said before, the arrangement affects the geometry and so on. A rotation table was needed, so the pulling point is only in one point for both robots, and as well the extrusion is placed in between the two robots to facilitate a faster process. So the process starts with a predefined position where the choreography can take place into all the points in space desired for the pulling. The tetrahedral position is also predefined. We have two end effectors, pulling end effector of the tetrahedral and picking up as well, and the plate end effector is only connecting an existing pulled in space beam. The extruder is static in between the two robots, and the process starts by picking up the tetrahedral. Then the robot goes to the extruder to extrude the material on the face of the picked tetrahedron. The control of temperature of the extruded material is really important because it affects the structure of the beam that is being pulled by the robot. Once the extrusion process is done, the robot goes to the predefined anchored point and start pulling the iterations. The speed and the angle at which the robot is pulling the material is really important. And this is where accuracy of robotic arms come in hand. Freezing is manually at this point, but we integrate it automatically later in the system. The end effector, plate end effector, is used to connect two existing nodes in space. And then we freeze the material instantly. Within seconds, it sets solid. Now, when able to join the two existing solid plates, we just use heat on one surface of the existing pulled beam to join the two nodes manually.
We continue studying the robotic configuration, which is the optimal configuration of the robot regarding to the parameters. And we have units. The unit size is very important. Our unit size is usually 1.2 to 1.5 meters. So we consider this as a working space. As long as we are using as well symmetry, it's important for us. We are using a rotation table, so the robot doesn't have to move in space, rather than the model is moving around, so it can reach more easily a certain position and can achieve the movement needed. The robot size, it's important to define which is the distance in between the working area and the robot, and we started to try to figure out by the different models and sizes of the robot to see which one is the one that is needed for our fabrication. The large-scale model seems to be the most, the best one in order to achieve our movement. And as long as we have the two robots, the extruded placement needs to be equally divided in space, so the robot can reach it. We divide equally the space for the two robots as well. Saying that, the cell that we are trying to achieve seems to be 6 by 4 by 3 meters, and it's like the optimal configuration that we need to do our units and to fabricate.
So, we're aiming to shift this paradigm where industrial robots are being used in factories, produce building blocks, and those building blocks are moved to site, and then on site it's assembled by humans. Rather, we want to fade away this line in between and bring it all into one, where the material and the process of fabrication and the outcome is all in one. And a precedent is Gramercy Kohler, where the robot is actually building the architecture on site, and it's the factory as well. Therefore, knowing our optimal configuration that can fit into a standard truck and can be moved to site, once the truck arrives on site, the fabrication starts. And once the fabrication of the unit ends, manual workers assemble those units on site using heat only. The fabrication process is aimed to be as simple as possible. So in summary, our system can produce structures that are jointless and are self-bindable with minimum scaffolding and no formwork needed. All the manufacturing process is done in a mobile cell, and once the units are no longer in use, they can either be shredded down, refit into the system, or left to biodegrade and die. The biodegradability of the material can vary according to usage, either 45 days to 4 years. Approximately, it takes 2 hours to produce 1 meter cube of space with our material. So what can we do with this automated robotic fabrication system? Due to the material phase-changing property and can produce different kind of nodes and different angles and different directions, along with the precision of the robot and the facility that the robot can produce, and the intelligence of the material, we're producing lattice structures that can be assembled on site using heat only, that can, for different kinds of activities, restaurants, galleries, spaces, pavilions, and so on. So as a prototypical approach, we chose a restaurant and a performance space to demonstrate our system.
We generated a prototypical application of our system on the restaurant in the Covent Garden Market in front of Russell Street. In order to generate relation with the Opera House building, we extended the design area from the terrace to the square. We took in consideration the main circulation that happens in the square, and we focus our attention on the circulation that affect our design area. According to this circulation, we defined anchor points that we use to define the boundary of, and the opening edge of our geometry. We introduce closed boundaries that generates new anchor points, and we generated a circular pattern that gives us the control on the length and the distribution of density of nodes, generating the 2D initial pattern. Then we relaxed this structure in order to respect the material behavior that needs to work mainly in axial forces. As we can see, we are achieving a network that is mainly working in compression and in tension. Tension happens mainly in the closed boundaries. We are controlling the parameters of this relaxation, taking in consideration the maximum length that material can achieve. So we relax the system in order to keep the maximum length in 60 centimeters. At the end of this process, we are evaluating and we are controlling the angle distribution. That is another important material parameter for our system. And we can observe from the map and from the diagrams that the distribution is changing according to a 5% value. So it is perfectly feasible with our material parameters. In order to fabricate our system, we subdivide the geometry in fabrication units that will be assembled by hand. The assembly process starts from the anchor points and grows radially in order to complete the wall structure using temporary scaffolding points.
So in summary, the mobile cell moved to different kind of sites. And in our case, it's moving towards Covent Garden. Once the cell arrives, the fabrication process starts. Then the fabricated units are assembled manually on site. The units are assembled as on the pattern. And then the structure is achieved. It's used heat only, so it's a monomaterial, completely integrated. And this is a prototypical scenario of the application. Once it's done, it either biodegrades and produces biomass, or it's refed into the system and moves to another site. And thank you.
This is one of our initial experiments while we were using the rigid plates, and it's still not, we still didn't achieve the continuity of the material. Then these are some special primitives and explorations that we did to achieve the angles. Then the material experimentation helped to continue with the digital. This is a design proposal that we see it as a prototypical example of our system. These are some of the spatial primitives, and these are our end effectors that we were using for the fabrication. Here we demonstrate what is the minimum and the maximum length of the beams with our material, and this is the fabrication that we did in RoboFold with Greg, that we have it here. That it's in 1:1 scale model, and it uses completely robots to fabricate. Thank you.
Very fascinating, and a lot of work put into this, and also great that you achieved to realize something, a real prototype. I'll maybe directly dive in some questions that hint at the structural kind of constraints that you might have. Is that you made a comment that you optimize it to reduce the tension in the elements, but the shape of the profile is actually best in tension, not in compression. And that might actually, that is a very non-typical thing. So imagine optimizing a column where you try to have as many tension elements as possible, because your profile suggests that. So that might be interesting to explore that. Also, when you look at the prototype that you did with at RoboVault, then you see that gravity plays a big role in during your extrusion. So perhaps it's more relevant to optimize your discretization, or how you cut up the pieces that you will assemble on site, in having them as much aligned with gravity in the workshop, so that you can control your geometry, right? Or otherwise, I would expect that you need to take these, you were talking about material intelligence. Well, that is perhaps a part of the material that is kind of dumb for what you're trying to do with it. So then you would need to take that into your simulation as well. And then I just want to comment on one thing that you said, that it's formworkless or false workless. Well, that is, I challenge you to build a shell formworkless. So perhaps another thing in the discretization, not only to control the geometry in your extrusion, but also to consider what would be the best way to assemble it in stable sections as much as possible, and to reduce the false work. But of course, that is a very, very hard problem. But just as a comment, that it's not entirely formworkless. But anyway, so I mentioned a few things that perhaps you could consider, because it might keep your geometry closer to what is really what you're optimizing structurally, right? Otherwise, you have to redo your entire optimization.
I wonder if I think it's pretty amazing that you have these prototypes here. First of all, it's pretty incredible to see. There's a sort of a narrative in the project that's related to sort of in situ fabrication. You spend a lot of time talking about this kind of cell that shows up on a site with these two robots in it. And for me, that's less compelling right now. It almost seems like it's not really necessary, per se. I mean, this could easily just be built in a studio and kind of brought to a site. And as you've mentioned, there might be efficiencies to that. And I can't help but wonder, you've been so, maybe it's because I've been staring at this clicking machine, which seems like there's been some real innovation here and the kind of the end effector. I can't help but wonder if there was another project here that would kind of question the industrial robot arm, actually much more fundamentally. At least for me right now, I know that these are doing complex things, but really when I get into it, I can actually replicate much of this motion just with my arms, and maybe some very simple motors that are angling, and it just seems like the innovation here could also begin to take on a kind of a machine design, a kind of a creative machine that could in fact be in situ, that might create a component and then slide along that component, create the next component, and would begin to kind of quite literally fabricate this in situ. And again, I'm fantasizing about a kind of machine that doesn't exist in the world. But I wonder if really to produce the kind of project with the narrative that you're after, that it really is going to take kind of much more machine innovation at a kind of more fundamental level to really question the technology much more fundamentally. That being said, you've done a lot with the industrial robot arm, but I think at a certain point, I think in the presentation, it was just sort of, it kind of kept going and kept, and at a certain point, I felt like it would have been productive to kind of break and kind of question that. It's clear that you've done some of that, and I, but couldn't help but think that would have been a potential avenue, let's just say.
Can I really quickly to follow up on that? So these extrusions are much more controlled. They're linear. They go with gravity. That's the point I made earlier. But then what Jason is saying is that, are you really doing much more by not, for example, positioning with a robot very exactly where your node needs to be, and then fuse it directly on site? And so think of not necessarily a module that doesn't necessarily work with you, and use a robot in a very different kind of situation. Anyway, and they could then also be the temporarily scaffolding during the assembly. So perhaps.
Just a few points. The first point I want to just make, congratulate you, not only on the research, but on the amazing presentation format. The didactic, every single slide full of videos and sequencing of graphics and making that plastic. I mean, I've just been reflecting on about the economic value of just this presentation. You don't want to know, really. I know what it takes. I mean, it's really, really stunning, and I think there is a general comment which I think is amazing in DRL, this cycle, the professionalism and compelling presentation material, really, really striking. Now, in terms of the content of the work, I mean, I think it's very, very intelligent and great, and I think there is merit in picking up the robot and running with it, because it's a ubiquitous piece of equipment which deserves to be exploited, and you entering a research community was trying to do that. Although I agree also there could be other spin-off machine inventions, most probably less likely than to pull off a real realization. The same with the quadrocopters. They're usually kind of picked up on items which are available and become available and are ubiquitous. I think it's very bright and intelligent. Now, specifically on the project, a number of comments. First is, the more you create these primitives and more symmetry and repetition they have, the less they require this particular mode of production, which is all about unique elements with the unique variations of angle, length, maybe material, quantity, and so on. So I think that the final project validates that. Where some of these, you would kind of then question that method and think of casting and more traditional mechanisms and ways of working. So, but I think, and if you take that seriously, that approach, and I think there's a lot of lovely elements to it, the biodegradableness, only 60 degrees of melting. By the way, don't do this project in Qatar or and South Africa, so there's climatic limits to that. But I was been thinking about the strengths of this and the profile of this and the structural capacity, which you started talking about, with its tensile and compressive strengths. By the way, it's great to maximize tension members, but somewhere compression has to go. So then you would have to introduce another element altogether, which picks up then that concentrated compression in the system. But I mean, there's a lot of weakness in this. This has a moment connection, so it doesn't need triangulation. That's one element we know, but it becomes quite weak in compression and tension, and in torsion. It's incredibly weak. So I think what I would question here is that idea of a single pull, single operation. You already have robots doing other things. You have the cooling. By the way, you need a third robot actually to hold this, unless it becomes, because as we saw, when the robot pulls off an existing lattice, which is at that point maybe soft, the whole thing distorts. Might become an interesting element in the process, but I think the third robot just keeping that, locking that will be another point. But my point is really this. The element doesn't need to be that pure. It doesn't need to be a single pull. I mean, I think for me, this element creates some kind of the webs of an I-beam, or if you now print flanges, or another kind of pulling of a flange element across that, then you get something very, very strong. And still, obviously, it's never an ideal optimized element, because you have these constraints which give you the flexibility in the machinery. So that's also worthwhile to be reflected on. What would be if you had that lattice, what would be kind of optimized ideal or various ideal geometries which this element should have at that point, and what are your constraints, and how far do you approximate this? And that I think that as a statement of method would have been necessary, rather than just kind of living with the relative dysfunctionality, or not measuring it against a more idealized geometry.
Sorry. Can I just add to that? I think your presentation was brilliant. I really like the way you present, and somebody's already said it, and I like your modeling. The thing is, you very quickly moved from understanding the material to what you can do with it, without really exploring a bit more what the material can do. The fact that you can get a material which you can reduce from about 60 degrees, you can reform it. You can make it into a number of forms. And when you look at your model there, it is clear that, and even these models, it's clear that it's taking compression, already been mentioned. It can take bending. You only concentrated on tension. Now, every form of building will either take tension, compression, bending, torsion, all of those. Your material, from what you've started with, can do that. And you haven't explored that. Having said that, the way you've presented your work and the forms you've tried to create with it are quite complex forms. So within the complex forms you're trying to create, you're then limiting your material in terms of what it can do. So I do believe that moving forward, you need to go back a little bit. You need to step back a little bit and actually give a bit more information as to what this material can do. You want the material intelligence. Explore that material intelligence. Once you've explored that, it means that your form itself are no longer limited. You can then create a bit more with that form. I mean, even when you look at this, is it going to be cladded or is it not going to be cladded? Nothing's saying your material cannot clad it in its form. And I think also what was mentioned, the fact that why not have something that's continuously fusing? You're using a robot, the temperature you need, you can cool it. The temperature you need to deform it is quite low, so there's nothing saying that even as it's continuously being built, it can be deformed and formed. See what I mean? So I think there's an opportunity here where you're missing, there's a whole section of the work on the materiality of what you're using, which you can explore a little bit more. That'll be my, contribution to this. I think it's a fantastic piece of work, and I actually like the fact that you're actually doing something with it. So you're creating a form with it, and that form, where you're limiting yourself, you can do a lot more with it.
I'm going to add a little bit to this. What strikes me in the project, and I don't know if I will be able to explain this in a proper structural way, definitely not. But yeah, exactly. Please do help me. What strikes me in the project is the great quantity of symmetry that I see around. And I immediately wonder, why could these elements not be prefabricated if there is so much symmetry indeed? And wouldn't it be 10 times more efficient? And so, yeah, back to the material qualities. For some reason, somewhere along the project, to me, it became monothematic. The explanation, as much as the graphics I liked, but after the first 10 slides, the graphics became also repetitive. The idea of the biodegradable, reusable is repeated 50 times during the presentation. The elements are repeated 200 times in each model. And I don't know, there is something that fundamentally doesn't work. And it has to do with this repetition and the willingness to still advocate for a non-standard mode of production that will be done on site. For me, there is a major contradiction in the project and the way it is presented. The way it is worked out and the way it is presented. So, having said that, I think that you have to reflect on this, because I think you still have in the project all the elements to make it more coherent, but you need to stress exactly the non-standard, exactly what it means to fabricate on site. What exactly is this? And at the moment, I don't see it anywhere. Let's say I don't see it, at least the way it's been presented today. There was at the very beginning, when you were advocating for the plastic architecture, there was this one slide in which you were pulling a line as opposed to one single vector. Let's say you were pulling a surface of plastic. There was this beautiful slide that you had of 3 layers of line being pulled into a kind of a surface made out of ridges somehow, that I thought, well, there is something there that has to do with material quality, has to do with a new form of making, and eventually exploring also the potential of the material qualities in terms of the holes. You were also saying, depending on how much material you put on the plate, how much stickiness you have on that plate, you can create holes in the pool. Nothing of that is back into the project. And I have really a huge problem with it. So, as much as there is a lot of work, and I congratulate you for that, I have a lot of reservations about the project.
Perhaps on a more positive note, I'm very excited about the promise which was present in both of Shajai's groups, you following of this idea of the monomaterial project, and you make a stronger argument, in fact, for this kind of reusability, life cycle things. But part of the ramifications of that, of course, is that now we operate in a way where we're just borrowing material. And if that's the case, then we actually have an economy of excess. And I'd love to see, in fact, that you completely contradict this material efficiency paradigm and say, no, because we can give this to the next guy, then in fact we can be incredibly indulgent, and we really don't have to try to make it small at all. What we do have to optimize is time on site, of course, and this is where there's the contradiction in the project. But we can actually put enormous amounts of material there and do things. Not only that, but of course, very rightfully, you went a really long way in optimizing and refining your specific process and using the robot, but the material itself, in terms of its possibilities that it lends the project, can be thermoformed, can be machined. There can be a whole series of secondary operations, all of which could be roboticized, that could add to that idea that, okay, fantastic, we can have incredible surface ornamentation, we can deform things that could completely, doesn't have to be a lattice at all, it could be completely enclosed because we can just slump a sheet on top of this form. And I think these things would really drag out this idea of, okay, fantastic, monomaterial project. For once, we can actually responsibly, crazily, right? Everyone, as soon as you say plastic, you think, God, these guys are evil, we should send them wherever. But in fact, you can flip the argument, and you have convincingly done so, but take more advantage of it.
I mean, I think these comments are quite important, and they're important in a sense because there's always been a kind of promise that industrial robots are going to give us all of this kind of freedom. What I like about the project is I think a lot of the things that Marta is bringing to the table are true, but at the same time, I think the restraint in terms of working, when we talk about optimization, we have to optimize machine time. There is a reality of the time it takes to produce something within the limits that we actually have. And I think part of the decisions, when it started off in more free-form experimentation, I think a lot of these early studies were there. I think there is a response in terms of some of the demonstration, and if this is treated as a final project, then I think that there's a lot of things that we can discuss on many, many levels to suggest that there is a finality. What I like about the issue, and particularly about the constraint of the machine, is that building and understanding things just like the temperature and the extrusion, it's not about that really being literally the extruder, but it's really building a kind of knowledge for the students to sort of operate with. Because in this kind of project, time sensitivity is such a calibrating element to the material properties, to the elasticity of it. And Albert's point about this deformation, reformation, even the issue about scaffolding. The material itself could be the temporal scaffolding strategies so that you start to reinvent really how you deploy this. I don't think the on-site aspect matters, but I do think the whole idea of the erection sequence, the processes, have to explore that same materiality to achieve the things where the formwork is not another material that's lost, but is actually ground up and maybe becomes the issues where we start to work at very different resolutions. I like the scalelessness of the material itself. If we look conceptually across the models, where we could see some of these like representational, smaller scale dome models could actually be ways of addressing surface. Where then, for example, thermoforming like Dave is mentioning, using the same heating processes, could be used to create enclosures. So I think that there's a lot of things in the project that can open up new trajectories, and I think it's really important to allow that project to actually flourish on that level. Because I think if we finalize the project, like in the renderings, I think they give a visualization of a glimpse. But for example, it is not really a shell structure. It works more like some of these space framing strategies. It is a constraint of time to sort of explore all of that stuff, but you know that somehow it's predicated on models that you guys have been developing with Albert and Ed. So I think the ideas of actually using it, and what I really like about the models of the videos of the actual robots working is because they seem to be working on something where serial repetition, because you see these kids struggling to pull two faces off. They may have done a little bit of lightweight exercise, but at the end of the day, to achieve this really high resolution space, it demands a sort of process that makes that really not craft-based in a traditional sense, but really robotic craft and sensibilities of actually thinking and thermoforming and reinventing plastics in architecture is a really important thing. It died in the 60s and 70s, and now it's readdressing itself. So even the nature of the material that we're looking at, of course, we could be using this material, but it could also be a proxy material for other forms of plastics and other forms of composites. So the process, I think, could open up a different level of interrogation and inquiry if you guys allow it to. And I think because you have 3 weeks to reflect on this, it's really important to take all of the comments on board, the good, the bad, the ugly, and to try to synthesize that in terms of how does that work for yourselves, because I see this as the first pass where you start to actually spatialize it and apply it. But the second pass, I think, is an intellectual one that really has to scan through all of this and actually give and pull out the moments that are really not just novel to you guys, but are really sort of contributing to the larger conversation about robotics and architecture.
I think the work, being involved in the work you've been doing, I think a lot of the work is already there. If for some reason you've missed out the idea on the materiality, what this material can do beyond just its linear form. And I think by actually bringing that into your work, you have the time and you have a lot of the information to bring that into the narrative of what you're doing. And that will deal with a number of the issues of the comments you're having today.
From my side, first of all, congratulations, fantastic presentation. Finally, something was happening on the table here. I was really happy, even though some people got annoyed. I do have to agree with Marta a little bit. In a way, I'm also irritated by the linearity of the work you presented. And I think Jason said something very important. I mean, you know, the robot can do this, but the robot can also do that. So I got really excited when you talked about reversibility. That is something also in the project before, the idea, can we find applications that are not so linear, ending up in a spatial stiff structure, but that are literally reversible. So in a sense, it's about machine innovation. It's also about material innovation. How can you combine those? How can you integrate those? Why is the actuator of the phase changing not integrated into the material? For example, why do you have to externally heat it or cool it down? Why cannot it be integrated into the material, therefore becoming reversible? So more kind of an integrated approach. that allows the versatility, because I think that's a really important word that hasn't been addressed for my kind of idea so far.
And to sort of build on that, I'm really curious, well, again, as a part of the narrative, there's this idea that it's recyclable, that somehow it's going to be taken down, and yet in the presentation, really, you're not actually you're showing us the kind of fabrication and assembly process, and it's very perfect on this site. But the other half of the story is in the 1 year later, when this needs to be taken down. What is in fact the strategy? You're going to go in with a chainsaw and just dice it up and remelt it, or is in fact maybe this wants to be reused on another site? I don't really know, but I'm super interested in that, and I wonder whether, and I don't even know if this material exists, but if there's another material, a second material, that maybe had a different melting point, right? So somehow imagine there's nozzles on each of these nodes that you can connect a hot air nozzle into it, and it would literally just melt that node. You'd be able to lift the components out, very readily lift the components out and reuse them on another site. And so that's why I'm not totally convinced that the single material is really the right thing. I think there's a lot of innovation that can really happen if you just play the story kind of all the way through. There could be incredible opportunities to run electricity through these things, and all sorts of lighting effects you can begin to imagine. I think you could really, begin to push this much further. And I don't know why it needs to be, single material. I think there could have been a fundamental sort of questioning of that, and it could have really opened up some opportunities here.
Couple of points.
Yeah, I think first of all, I would like to commend you for being so almost anal about working out working out all the details. It's not easy to go from something that's there, clearly problematic thing, to seeing something that is on its way to being worked out. And the fact that all the comments are focusing on nuance and detail, to me that is a direct reflection of the fact that you've really taken on board trying to work things out, not only on the material side, the robotics, the scale, and so I think you should be commended on bringing that to the table. All the other things are now possible because all the base work is kind of done. So for your book, you should now take the opportunity to reflect on all the comments and see the potential further architectural application. As Theo said, that shouldn't be the final project, because the projects that all this research enables is way more, and I think that's what you should take away for the next 3 weeks.
Yeah, I also want to congratulate you on a great project. So it was a pleasure working with you all, and I was lucky enough to see sort of behind the scenes of how this all came together. So the presentations have very much been focused on the output, but a lot of the previous presentations we've seen have actually shown us really how the structures and architecture was manifest, so how the prototypes were made. And I think by avoiding sort of fetishizing the robot, in case you were criticized too much for that, you haven't shown us actually that you built a industrial system, really. So there was a full simulation of the entire assembly process. So it wasn't just stretching in one direction and orienting. There was a sequential process here with many, many stages. So I think you shouldn't be afraid of actually telling people about that and being proud that you've actually built something on par with most industrial systems. So you should be proud of that.
Okay, guys, we're going to need a really quick changeover. So let's grab them all.
no.